Let's say that we have this linear equation and two variables. Now, I am gonna write this thing a bit differently. This is still the same as our original equation, except that now it's written in matrix form, and now we are finding vectors x, y that satisfy this equation. After a bit of simplification and manipulation, we would find out that all vectors of the form x, 2x satisfy that equation. Now, I am gonna replace x with some parameter, let's say t, where t ranges over all real numbers. Now, the set of all solutions to our matrix equation is just all of the constant multiples of the vector 1, 2. This set is actually very important and has its own special name. It's called the span of 1, 2. Now we are about to introduce something big, but first consider two vectors that are in the span of 1, 2. If we add those two vectors together, we get another vector. Notice something, this vector right here is just a constant multiple of 1, 2 and remember that the span of 1, 2 was the set of all constant multiples of 1, 2. So, this vector is in the span of 1, 2. Now, we have just found out that if we add two vectors in the span, then the result is also in the span. But, what would happen if we add any number of vectors in the span? Would the result still be in span? If we expand the sum, we get this. Now, this is just a constant multiple of 1, 2, which is obviously in the span of 1, 2. We have now just proved that the sum of any number of vectors in the span of 1, 2 is also in the span. Now, we have to ask one more question before we introduce the elephant in the room. Is every constant multiple of a vector in the span also in the span? Well, the proof is quite trivial and is therefore left as an exercise for the reader. Just kidding. Actually, any vector in the span can be expressed as a constant multiple of 1, 2, and the span itself is the set of all constant multiples of 1, 2. So, of course, every constant multiple of a vector already in the span is also in the span. Now, we know a bit about the properties of the span of 1, 2. If we add any two vectors in the span, then the result is also in the span. This property is also known as closure under vector addition. If we multiply a vector in the span of 1, 2 by a scalar, then the result is also in the span. This property is also known as closure under scalar multiplication. Now, it's time to introduce the elephant in the room. The vector space over a set of scalars f is a set of vectors v with two binary operations. The first one is called vector addition, which takes in two vectors from v and outputs a single vector that also lies in v. This operation has to obey the following axioms. The second operation, which is called scalar multiplication, takes in a vector from v and a scalar from f and outputs a vector that lies in v. This operation also has to obey some axioms. There are two additional axioms that govern how scalar multiplication behaves with vector addition. Now, you may have noticed that we are adding two scalars and also multiplying two scalars, so we need to have addition and multiplication defined on f. So, f needs to be a field. If you don't know what a field is, don't worry, we are only gonna use the set of real numbers as the set of scalars. Now it's time to get back to the span of 1, 2. Actually, the span of 1, 2 with a set of scalars defined as the real numbers is a vector space if we define vector addition and scalar multiplication in the normal way. In general, the span of any vector, the set of all constant multiples of that vector, forms the vector space if you define vector addition and scalar multiplication in the normal way. I recommend that you review the vector space axioms and prove it yourself that the span does form a vector space. Now, we will end this video by taking a look at systems of equations of the following form. Actually, we can write this system in a much simpler form if we use matrices. Let's say that x1 and x2 are solutions to this equation. Actually, if we add those two solutions together, we will get another solution. If we multiply a solution by a constant, we get another solution. Now, it will be pretty tempting to think that the set of all solutions to ax equals 0 forms a vector space. And you would be right, it does form a vector space. We are gonna stop right here in this video. In the next one we will explore and visualize systems of equations and their solutions.